就是可以上课。那个是哦，这样没啦。好，那我们开始上课。So, last week I was talking about chapter 8. So for this week, I will do my presentation for the research. So currently I do the research is about the colon anatomy localization. So it means like localize the colon anatomy in the colonoscopy. So this is like related with the medical imaging. Oh, okay. So let's start from the background and motivations of why doing this research. So the thing is, colorectal cancer, or which is cancer in the colon, is like among the most common cancer. So usually, what we call as a tumor or like cancer is called as a, I mean like the like some anomaly is called polyp. So this polyp can progress to precancer, and this precancer can progress to cancer. So to do this, usually doctor use colonoscopy. So this is like to detect and remove the polyps through the phases like cleaning, detection, injection, and resection of the polyp. And for this research, I didn't do the polyp detections. I do the colon anatomical classification. So I do this is because like the thing is there is still like significant where documentation about how where the polyp is located is very rare, like in the research. So for now, the focus is about documentation of where the polyp is found or any other finding in the colonoscopy procedure that essential for the diagnosis and reporting. And for now, is my focus is the colon anatomical classification, which later after got this colon anatomical of like the label can be used for the documentation where it can fit into the large language model for the documentation. So the goal is to identifying the anatomical colon landmarks. So as you can see in here, there's actually like 10 landmarks that can be classified as the colon anatomy, and they all looks very similar, like the pattern, like this triangle pattern. So the most important thing in colonoscopy usually in the cecum. But for this part, I want to try to classify, like the result is that cecum, ascending colon, transverse colon, sigmoid colon, descending colon, and the rectum. But to do this, I only use like 5 landmarks, which is the cecum, and then the hepatic flexure, the splenic flexure, the sigmoid colon, and rectum for later being assigning the segment in the rule-based system. So yeah, still there is a challenge in this, which is like as you can see like in these images, it was like the visual similarity, like you see like all of them like look so similar. And another thing is that also the sudden frame transition that can cause unstable prediction in the colonoscopy video. So such as like the also like featureless frame because we do in video. So there's a lot of blurry bubble cover and features frames that can reduce the accuracy because like if the model predict that thing, then it will predict wrongly, pretty sure. So that's why for the pipeline methodology in here, as you can see, I use around like 75 videos test colonoscopy data set for the training and extract the images. So the pre-processing is that it need to be filtered using the quality filtering. So this is to filter the images into the 6 classes, which is the 5 landmarks that I say about the cecum, hepatic, splenic, sigmoid, and rectum. And another class is ambiguous. So ambiguous is called as an uninformative frames, which is the frames that we want to try to avoid because we doesn't want to predict in that kind of frame because ambiguous is something like blurry, bubble, and this is the frame or like some, it's basically featureless. So we cannot use this as a prediction. So for that, there is like this class called ambiguous. And after that training, using the YOLO 11S classification, and this is gonna give a frame-wise model, like frame-wise prediction in the model inference in the video. And because of that, we use the filter bit decoding and also the hidden Markov model. And for after get the result, it will give like boundaries where we're gonna select the segment bit using the rule base. And yeah, after that we can cluster and got the result.
Yeah, the same thing. Her research, we will have 6 points in her research. Yeah, 2 points of the method and 2 points of the steps and 2 points of the results. Yeah, okay.
Okay. So as a single phrase wise prediction, as you can see in here, it looks like very flickering, and also don't you think it looks like very noisy, because like it keep jumping and like too many stuff, like for example, like if you see the mark over there, like probably secum jump to hepatic or like splenic and stuff. But the thing is, in the colon, as you can see, you need to respect like the order. The order need to be start from the secum, and then next is like ascending, and then next is hepatic, and then transfer, splenic, descending, sigmoid, and rectum. So this is the order of the colon. So you need to respect this, and that's why this kind of thing is looks so noisy, because like if you just do like the frame-wise prediction, it will never like respect the order, because like we don't have this temporal modeling. So that's why for the processing inference in here, I use the filter bit decoding and also the hidden Markov model. Yeah, but I didn't write it here, but yeah, I did it. So this is like to respect the anatomical order constraint, like what I said before. And in this case, that it can prevent like no jumping like from the sigmoid to secum. And after that, it will get, so as you can see in this graph, this is like basically like the after like it looks very messy, yes, but like if you, because like a lot of things in here is ambiguous, and if you see in here there's like a line, so this is like the boundary pick that we get after calculation formula from the filter bit decoding and also hidden Markov transition. Because in here that like the hidden Markov transition is that I set around 0.05. It was like the transition probability if we want to advance to the next segment. So I actually prioritize more that it stay, because I don't want it to keep like flickering or changing too much. So after we got like this peak in here, like the peak in here, this is like the secum, and then after that we got the hepatic, the splenic, and also the sigmoid and the rectum peak. Then we can actually do the rule-based grouping. So for example, like before secum, it will gonna segment as a secum, and then between the secum and the hepatic flexure, it will be ascending colon. And between the hepatic flexure and splenic, it will be transverse colon. And between the splenic and sigmoid is descending. And between sigmoid colon and rectum is sigmoid colon. And after rectum is rectum. So this kind of rule-based grouping is respecting the order on in here. So as you can see, like between secum and the hepatic is ascending, right? Like this part. Yeah. And after between the hepatic and the splenic is the transverse colon and the stuff. So yeah, this is the rule-based system. So after we got the boundary, we use like this to assign the interval. And the result is going to be smoother, as you can see, compared to the frame-wise prediction. So this is like, because in the colonoscopy video, it's from the beginning to the very end. This is like the withdrawer state. So from usually, it always the video start from secure. But okay, it's not necessary also start from secure, but most of the time I always start on secum. So in here, for this video case example, it start from secum. So secum, and then ascending colon, transverse colon, descending, sigmoid, and rectum. And we got like now the prediction for one whole video for the colon anatomy localization. And this thing later can be used for the documentation. But yeah, for now I didn't yet integrate the documentation. So yeah, the analysis that the limitation of this approach is to only assume that it progresses in one direction, as you can see, like one direction. But the thing is, in reality, some doctor, of course, like during the colonoscopy, they move back and forth between different regions. And another feature is like to solve this limitation above. So yeah.
The previous page, yeah. For this problem, no. Yeah, for this problem that the surgeon move back and forth. Let's go back. one page. Yeah, yeah. So it doesn't matter because as long as you dictate it, or the boundary here, even back forth, forward and back. Yeah, and it doesn't matter because that place can be defined as either this side or this side. So it doesn't matter. Yeah.
So yeah, basically that is the summary for the method, steps, and result, and for the exam. So thank you.
Okay, let's show a video, and then the next chapter 9. Now, what is chapter 9? Okay, so Namanta will present chapter 9. Yeah, like a joke video first. Yeah. Good. Okay, so ch8-9 is by Namanta ch8-9 and if you think he presents well, please vote for him before the final. Okay. Okay.
Uh,
Yeah, it is. I can hear it.
Hello.
Okay.
All right. Hello everyone. My name is Nam Anh Ta, and today I'm going to present the chapter 9, which is the motion estimation.
Have your mobile
Uh,
number. Yeah.
Okay. Wait a second. And on the screen is my contact information. So if you guys have any inquiries, you can contact via my information. So in this chapter 9, motion estimation, I have to warn you that this is mathematically heavy and you may find it a little bit stressful or something, but like we still need to deal with all of this. So this chapter, the chapter 9, so I will give you a simple roadmap here. So previous chapter, you might like focus on static images. So today we will explore how the computer vision can handle like temporal changes, basically like how things move over time. And this is a basic roadmap, as you can see. We will begin with the image processing, focusing on pixel level changes. And the second is the geometry-based vision or the geometric vision, which deals with the mathematical relationships of movements. And the third thing here is the physical vision, which involve the real-world physics of motion. And the fourth here is the semantic vision, where we can understand like what is moving. And finally is the motion handling, which we will explore right now. We can like, how can we actually like process and manage like this type of data? So in this chapter, we will break down the study of motion into four main themes right here. The first we will look at is the translational alignment, which is like the simplest form of tracking movement, like from one frame to another. And the next thing is the optical flow. And this is like the core focus of today's lecture. And we will spend like a significant amount of time in here in the second part, because like it's a fundamental, like how can we like estimate the motion of every single pixel in a sequence. And in maybe today, I mean, in this optical flow session, I will also release the third homework or the homework 3. And you might need like some materials in this lecture. And after that, we will scale up to the third part is the parametric motion, where we will use the mathematical models to describe like a more complex global movements, like zooming or rotations. And the fourth and the finally, we will discuss about the layer motion, which is like a more advanced technique used to like to separate like different moving objects from their background. Okay, so the first topic we'll discuss here is the translational alignment. And so at this simplest level, motion like motion estimation will start by finding like the displacement between two frames. So we are trying to like align or match like a set of pixels from frame A to frame B to their new location in frame B. And this is a fundamental building block for a much more complex models like we will see later. So we will see a short video right here. Please notice like, hold on, let me just see my. Okay, so let's look at like a more practical application here, which is like the face alignment. So the green outline on this person's face shows like how like these points can be tracked and aligned, like regardless like the person's head angle or facial expression. So we can apply like translational alignment to shift a face to a standardized position. So like from between each frame, you can actually still track those movements, like where the face is in these frames. Or you can see like in this case, like you can see like we can actually like track the from the green lines, so we can track like between each frames, like where the face of this person is in here. Or any other examples like this. So we will use like translational alignment for this. And another application of the translational alignment is video stabilization, which is like, for example, this is like a traffic camera we can like commonly used in highway surveillance. So if you compare these two frames, like the one on the right hand side, the one on the right is like pretty shaky, and the one on the right is after apply translational alignment, so we can like compensate the motion. So we can remove like any camera shake or vibrations by using these techniques. Because like the video on the right, on the left hand side is caught like because of the wind or like any traffic motion, you can see it actually like vibrate pretty terrible. So by using after like apply translation alignment, you can stabilize the video, and you can actually like track the vehicle on the road. So let's move to more practical questions here. How can we find like a specific target or a template within a given image? So to achieve the alignment, we need to locate like where our target object has moved. So this process is called template matching, and it's the most basic way to estimate like the translation between each frame. So we will start at a very simple math right here. Let me use a laser point. So the goal of the template matching is pretty simple actually. You need to find like the exact alignment between the two frames. Okay, on the left we will have a thing called the template image, and this is the reference we are looking for. And the right hand side is the target image. So the target image is like where the search will happen, and the template is the reference that we are looking for. So we will take a set of pixel coordinates from the template, and then we will find like where they move in the target. But like to do this in a effectively way, we need a mathematical standard so we can like judge the result if it's good or bad. And this is when we need a metric or error metric, specifically a way to measure like how wrong or right our alignment is. So how can we like mathematically define like a good match between two frames? So the most basic way is using SSD here, or sum of square differences. So our goal is to find the displacement of the vector u here. So when we want to shift the image, so the difference between two frames, which we'll call the error EI here, as small as possible. But to make this work, we need to rely on a very important assumption called brightness constancy. So we assume that even if an object moves, its brightness and color doesn't change between each frame, as you can see in this formula in internal form. This means that like the pixel value of the new location in the frame one should be like identical to the original value in the frame 0. And this isn't just for the SSD. This is actually like the core foundation of the optical flow, which we will discuss later. So beyond the brightness constancy, actually SSD or sum of square differences is actually pretty sensitive to the outliers. So how can we actually solve this? Because as you can see on this plot right here, the red line represents the mean square error, and it actually like for the training data is actually the mesh for that line, because like the SSD actually like pretty sensitive for the outliers. So because in the real world scenarios, we will deal like with noise, like occlusion or like the object moving out of the frame, and this thing will create outliers. So if we stick with the SSD, this error might get square and completely ruin our motion estimation. So to fix this, we will need a robust error matrix right here. So first thing first, you need to look at this SRD, or sum of robust differences. So instead of squaring errors as we like usually do, we will pass it through a robust function called raw, like the p character here. It look like p, but it's not p, it's raw. So as you can see here, like yeah, it's a Greek letter, looks like a p character, but it's not. It's raw. So as you can see right here, if the arrow grows, will the penalty doesn't explode it because we doesn't use the square function here. So it might levels up a little bit, meaning that the outliers won't dominate our calculation. And another common alternative is the SAD, or the sum of absolute difference. Sum of absolute difference, or you might heard it as the L1 norm. This is actually much more stable than the SSD because like when we dealing with more like extreme values, um, but this has like a mathematical drawback right here because like it's not differentiable at the origin, which means that like it's a bit tricky to solve because like you just cannot use like simple gradient descent as we usually use. You need like a much more complex methods like the subderivatives. So to get the best of the both worlds that I've just introduced, we will use a smooth, robust function like the German Makler. So sorry if I'm pronouncing it correctly or not. So the idea is actually pretty simple. This is a function, and this will act like the SSD to give us like precise alignment. But if the arrow grows, the function will levels off that outlier, so don't take like the takeover. So the key here is they use a parameter a right here. So the parameter a will act like the outlier thresholds. Instead of picking like a random number, we often set it like automatically by using like 1.4 times the math or the median absolute deviation. So by using the median instead of the mean, our threshold becomes like much more resistant to the noise. So we allow the model to adapt to the actual error distribution of our data. So to make our estimation even more like yeah. Okay, so I will pause it right here on the 13th slide. Hold on. Recently I really like this guy. Like,
Okay, got it.
All right, let's
Yeah.
continue. Okay, so I will continue from this. Like by using the median instead of the mean, our threshold will become like more resistant to noise. So this will allow the model to adapt to the actual error distribution of our data. So to make our estimation like even more robust, we will use like the weighted SSD or the weighted SSD. So we will apply the weight like the W0 and the W1 right here. So we will apply this to each pixel. So if a pixel moves outside the image frame or belongs to like to some noisy regions or something, we can set its weight to 0, so it doesn't like corrupt our result or affect our results. But like this also led to another problem. So what will happen if the movement is too large? So if the object like jumps further than our search window, like standard local meshing, like it will fail. So we will need like more advanced strategies, or like the cost to find approaches to handle like these large displacements. And the root means great. Okay, so a common issue in template matching is the bias from the overlaps. So if only a few pixels overlap, the total error like it might look small even if the match is wrong. So to fix this, we need to normalize the error by the overlap area area A. So by calculating the RMS error or the root mean square error, we can get like the average penalty per pixel. So this will ensure a fair comparison regardless like how much images overlap. And this actually is especially important when we using like image pyramids or multi-resolution matching. Pyramid.
Yeah, pyramid.
And in practice, images often have like a different lighting or exposure. So to handle this, we will use the bias and gain model. You might heard of this before. So instead of assuming like the intensity are identical, we model like the change linearly. So here, the alpha here is the gain, which adjusts the contrast, and the beta here is the bias, which accounts for like for a global shift in brightness. So by solving for these parameters along with the displacement, we can like achieve a more accurate alignment, even if like one frame is significantly brighter or like brighter than the other. So to solve for these parameters, we can plug them into the mean square error formula right here, the mean square error, like the square one here, and use the linear regression. And this ensures that the alignment is driven by the actual structure of the image, like the actual structure, not the exposure changes. So you may find these techniques in MPEG or MPEG encoding for weighted prediction, and it can even like be applied to each color channel separately for more complex like lighting scenarios. So instead of looking at the difference between pixels, we can actually use cross correlation. And so in this approach, we will multiply the corresponding pixels of both images and then sum the results. So the idea is actually pretty simple. If the features in both frames align perfectly, the product will be like very large. So giving us like a high similarity score, it's called a similarity score. So this is a very effective way to detect if a pattern exists in a specific location, regardless like the exact brightness levels. So a small comparison here is the between the convolution and the correlation. So for the convolution right here, for the convolution operation, like the kernel or the filter will be flipped horizontally and vertically before sliding and calculating before calculating like the dot product. And for the cross correlation, the kernel is slit like directly as it is without any flipping. So we can perform like the element-wise multiplication and summation. So, and another thing I introduced here is the autocorrelation, which matching like a signal of an image against itself. This is actually pretty useful for finding like periodicity or repetitive structure. So why like the cross correlation is actually pretty intuitive. It has like a major weakness because like it is like easily like biased by like wider regions, because like a very bright spot in the target image can be produced like a high score even if the pattern doesn't match at all. So to fix this, so how can we actually fix this? We will use the normalized cross attention or the NCC. I will introduce the NCC. So by normalizing like the mean brightness and contrast, we can ensure that the algorithm focus on the underlying texture and shape. So this will make like our alignment become more reliable. So it will be fooled by the local lighting changes or hotspots in the frame. So to understand the math behind NCC or normalized cross attention, we can look at the core concept right here. This is actually a pretty mathematically heavy as I warned before. So we were performing zero mean normalization. So by subtracting the mean intensity and divide by the standard deviation, we can actually essentially make the matching process invariant to lighting shifts and contrast changes. And one of the best features in NCC is its output range. So which is like strictly between the negative 1 and 1. A score of 1 means that you found a perfect match. However, like you will need to watch out for the flat regions like a clear blue sky or a plain white wall, like some structure like that. Because like in these areas, like a completely clear blue sky, the contrast is like nearly zero. So which make like the denominator right here in our formula nearly like approach to zero. So this can cause like numerical instability. So in practice, we actually like often add like a small epsilon value right here, like plus epsilon right here to prevent. So the denominator will to keep the denominator won't reach zero. So the system become like much more stable.
Yeah, divided by zero.
Divide by zero error.
Yeah.
We need to add like a small epsilon right here to prevent like this divide by zero. And another thing here is the normalized. Yeah, the normalized is still like this is. So back to this problem, how can we find the optimal alignment between like this small region to the entire picture right here? So because like all the things I actually introduced before is all about the error matrix. So because we define our error matrix to compare two images. So the next question is, how can we search for the best match? So the first idea right here is like template matching when we like comparing like pixel by pixel. If we can actually like compare like pixel by pixel, but that attempt is actually like too slow. So is there any other like more efficient method? We will have the second idea here is the pyramid template matching or the cost to find. So the problem is like matching a small patch, like because like the thing that I want to find here is like the eye. So if we want to match a small patch right here, like against every pixel of the full resolution, it will be like very slow. So the solution here of this method is to downsample the image to create a pyramid. And then we will start matching up the lowest resolution right here. And then this is the coarse level to find like an approximate location. And then we will gradually move to higher resolution right here, which is the fine levels to refine the position. So the benefit here is this is actually like much faster and avoid like any local minima while like we can actually still maintain the accuracy. So we can actually like generalize the pyramid concept into what I just call the cost to find motion estimation. So because I will tell you why we need this, because like if an object moves very fast, like 15 pixels between frames, like move very fast between each frames, a local search window, it will be completely missed it. So if we shrink that image to down to several levels, that 50 pixel jump will becomes like only only 2 to 3 pixel shift. And at this cross level, the algorithm can actually like pretty easily capture the general direction of that movement. So when we can have that rough estimate, we can propagate it into the next level up. So in short, we can actually like we can use low resolution for global coverage and high resolution for pixel perfect precision. But there's another problem in this second method, this pyramid method, this information loss. So when the pyramid structure actually speed up the estimation, excessive compression can cause the image features to vanish. So when once the image become like a little blurry, like critical details like the contour or the edges, which are like pretty essential for the alignment, it will be lost. For example, like some image like the zebra right here, or an artwork of Van Gogh right here. It has so many like distinct structure, like different from any other structure, because it has so many like the boundaries and like contours, like edges. So if we downsample it down to a cross level, those information will be lost. And when we use a fine level to align it perfectly, it will be miss those information. Because like for example, in this zebra, this is a zebra nose, right? When we downsample it in this pyramid, the zebra nose that are like nearly erased at the lowest resolution. You cannot see anything. Even to me, I cannot see anything right here. Yeah, we cannot see the zebra nose anymore. So if this is a problem of this pyramid method. And next up, we will move to from the spatial domain to the frequency domain. We will discuss the Fourier-based alignment. You might heard of this before. You definitely have heard of the Fourier transform before. So this was proposed by Fourier, stating that like any function of a single variable can be represented as a weighted sum of sines and cosines of different frequencies. So this will allow us to describe any signal, including image signals, using a combination of simple waveforms. And this theorem forms like a mathematical foundation for the Fourier-based alignment we will discuss today. So here you might see the Fourier series before. For example, this is a square. This is a square wave, right? We have a square wave right here, but we can actually like decompose this into multiple set of sine waves. So because by superimposing sine waves of like different frequencies, we can actually approximate like any waveform shape. So like in this case, in this upper case, you might not notice that is any difference, but like in the illustration down here, we can actually like approximate this square wave to multiple set of sine waves. So this is noted that even complex waveform can be decomposed into much simple components in the frequency domain. So the actual math behind it is actually like pretty complex yet simple. So we will categorize the Fourier transform into two versions. The first one is the continuous one, and the second one is a discrete one. So the continuous Fourier transform is essential for theory, but we actually like more focus on the discrete Fourier transform, or the DFT, for our digital image. So the key component here is the complex exponential right here. This acts like a rotation factor you will see in the formula. It acts like a bridge that carries like our signal from the spatial domain to the frequency domain. Also, you need to notice that the Euler formula on the upper right corner, This reminds us that these complex exponential are it's just like a combination of sine and cosine. So in a more visual, in a more visually way, you can see we have two Fourier components right here, the amplitude and the phase. And this is the original images. The middle column here is the amplitude spectrum, which shows the distribution of frequencies in this original image. And the right column here, the third column here, is the phase spectrum. This represents which this will preserve like the spatial structures of the image. This carries like where and what of the image structures. So the key point here is the phase information is much more critical for image reconstruction and structural integrity. But so this is we will like prioritize the phase information when performing like image alignment. We need to focus on the phase, not the amplitude. So I just mentioned that the image phase matters, right? So why? We look at the image on the left. In this image, we will took the amplitude of the zebra, but kept the phase from the leopard. So even leopard.
Actually, over here is cheetah.
Cheetah, not the cheetah. Okay, this is the cheetah. So sorry. So we will take the amplitude from the zebra and the phase from the amplitude from the zebra and the phase from the cheetah. So the energy distribution belongs to the zebra, right? But your eyes, even my own eyes, still see that this is still a cheetah. So why does this happen? Because like the phase information will tell us like where the pixel will go to form edges and structures. So the conclusion here is we only care about the phase. We need to care about the phase. The phase is the thing that matters, not the amplitude. Okay, so before I enter to this Fourier based alignment,
we will take a break.
we will take a 10 minutes break. We will come back at 3:20.
Oh, wait a minute. Yeah. Okay. You are supposed to come to me for the term project presentation yesterday. Does anyone doesn't come to me yesterday? Okay, please come with me now. Yeah. Anyone who doesn't come, who did not come yesterday, please come with me to present your progress. Yeah.
有没有需要来前面看期中考卷？先是的一个报纸这边。
有所以买
I don't think we put it right.
你得不今天有了吗？ All right, so let's continue back to the lecture. So in this, there are some properties of this alignment of the Fourier the Fourier transform of the alignment. So the first thing is the translation property, because a shift in the spatial domain result only in the phase shift in the frequency domain, and the amplitude remains unchanged. And the second is the convolution theorem. The convolution in spatial domain is equivalent to the multiplication in the frequency domain. And this shows us this allows us to replace traditional spatial sliding with simple multiplication, and we can perform like cross correlation in the frequency domain. And the second thing here is the FFT, or the fast Fourier transform. This is the engine of the efficient alignment. So the FFT is a landmark algorithm that can reduce the computational complexity of the original Fourier transform. So the mechanism of this FFT, or the fast Fourier transform, is to use divide and conquer strategies to speed up the Fourier transform. So the process here is to take two signals right here. We perform the FFT, the fast Fourier transform, on each of the signal, this one and this one, and then so we can move them into the frequency domain, and then we will multiply these two signals in the frequency domain, and then we will apply the inverse the FFT, or the inverse fast Fourier transform, to return to the spatial domain. And this is like the most efficient way to perform like convolutions and making like large scale image alignment feasible for real-time applications. So how can we like bring our traditional like SSD sum of square differences into the frequency domain? So it will expand the SSD formula mathematically. We can find it consists of image energy terms and a cross correlation term. So by combining the image energy with a cross correlation result, we can calculate the total SSD for all possible displacement simultaneously. And this is like a massive optimization. So instead of the slow pixel by pixel spatial approach, we will use the power of the frequency domain to achieve like the same result in the fraction of time. Next up is a window cross correlation. So instead of aligning the entire image, we often focus on the specific regions or local features. So the mechanism here is the windowing. It involves applying weights to pixels within a certain range while setting weights outside that range to 0. We will have two weights right here, the W0 and the W1. So these two weights used for the reference image I0 right here to the target image I1 right here. So the energy is the cross correlation of the two weighted images right here. And it can be simplified as this. Next up is the phase correlation. So a frequency domain technique used to estimate the relative translation offset between two images. So the core idea here is whitening. So what is whitening? Whitening means that when we normalize the product of two Fourier transforms by dividing it by their magnitudes, keeping only the phase information. So in an ideal scenario, if one image is just a shifted version of the other, the only difference between two images in the frequency domain is just a phase shift. And how can we use Fourier transform to handle rotation and scale? So beyond translation, while we previously focused on finding the translation offset, real world image changes often include both rotation and scale, which is zooming. So this can actually demonstrate that the Fourier transform is not limited to translation. It can also be adapted to handle these geometric transformations. So by combining the Fourier transform with coordinate transformation, like the polar or the log polar coordinates, we can actually turn rotation and scale into simple translation problems. So back to this problem. How can we achieve a maximum computational speed for the real-time performance of this problem? So there are some mathematical notation for the image alignment here. I need to introduce first because I won't introduce that again. The first thing is the WXP here. This is a rough function. A rough function for 2D or 2D transformation. This will map the coordinate x to a new position based on parameters p. The x right here is the original 2D coordinates, and the p right here is a vector of transformation parameters, like the translation, affine, or projective. And the y here and the I here is the pixel value of a rough position. Then this is what we'll compare against our template image. So a quick review of the affine transform. This is like a linear transform that includes translation, rotation, scaling, or even shearing. It has 6 degrees of freedom, represented by parameters from P1 through P6. So the key thing to remember here is that affine transform preserve parallelism, making it a very robust model for 2D alignment tasks. So to align our images, we treat it as an optimization problem. So we will have two images right here. The first is our fixed template TX, and our input image I, and then we will wrap using a parameter P inside right here. So we want to find the best P that makes this I look exactly like the T. So we will measure the difference using the SSD, the sum of square differences. Sum of square differences. So for every pixel X, we can calculate the error between the template and the wrap image, square it, and then sum it up. So how can we solve for this P efficiently? How can we find a solution for this problem? So even though that our goal is pretty clear, but solving this equation is actually pretty difficult. So the first thing is the wrap function here is nonlinear, but more importantly, the image IX is non-parametric. So we cannot we don't have a mathematical formula for the image. We only have the image is just a grid of pixels. Because we cannot write I a simple equation, we cannot solve for the P directly. So we need iterative optimization methods so we can find the best fit. So the third idea here, back to this problem again, the third idea here is model refinement. So look at this phase tracking example right here. We selected a small patch, which is the I, okay, as our template. So the green arrow here shows like the movement needed to stay aligned in the next frame. So this is where the Lucas kinetic algorithm shines, like when I will introduce the Lucas kinetic algorithm shortly. So if your starting point is actually like pretty near to the correct location, the algorithm we can actually like very quickly and accurately fine tune the parameters to find the perfect match of this. So we are moving into one of the most foundational methods in computer vision, which is the Lucas kinetic algorithm, which was first introduced in 1981. So its genius like lies in how it treats like image alignment as like an optimization problem. So the core idea here is incremental refinement. So assuming that we already have like a decent initial estimate, like because like in this we assume that we already have like a nearly correct answer, but so in here assuming that we have like an initial guess key. So instead of solving the entire optimization problem from scratch, we only focus on finding a small adjustment of the data P right here. So the process is update the parameters from P plus delta P and convert and transform it into P, and then repeat this until the alignment is perfect. Next up, we will, because like this is still a nonlinear function, so we need to linearize the problem. So we will use this by using the Taylor expansion. Okay, not Taylor Swift, this is Taylor expansion. So the objective function remains like nonlinear due to the wrap function W right here. So because of that, we will use a first order Taylor expansion to linearize the expression and around the current parameter P. So by approximating the function with its gradient, we can solve for the optimal increment delta P right here using a simple system of like linear equation. So the main reason we use the Taylor expansion here is to linearize our objective function. So as we discussed before, the original function is nonlinear and very difficult to handle directly. So by applying the Taylor series, we can actually like approximate the image function around its current stage. And this transformation is actually like something like a linear algebra problem. So this is the linearization step include like the chain rule and the approximation. So the first line here, we will apply the first order Taylor expansion. So this assumes that the increment delta P is small enough that the function can behave like linearly in that local neighborhood. Okay, and then we will find the derivative with respect to the parameter P. With respect, and then we will use the chain rule. First we will take the image gradient. Okay, so this is actually like the nabla operator. Yeah, you might heard it before. This is like the change of intensity over the space. And second, we will multiply it by this part. This is like the Jacobian of the wrap. This is how the coordinate change with respect to the parameters. So the result here is this simplification transform of the objective function into a linear form, which will allowing us to solve for delta P using like standard linear algebra. So through the Taylor expansion, we can transform like a difficult like nonlinear problem into a clear linear system. So all that remains here is like to solve this as a standard like least square problem, like the least square problem. So by setting the derivatives with respect like delta P to 0, we can directly compute the optimal adjustment needed for this iteration. So, and this is the reason why like the Lucas kinetic is so powerful, because like once we are in the linear form, we can solve for our 6 affine parameters. or any other raw parameters using simple matrix inversion. We will then update our position within a few iterations, the algorithm converges to the exact alignment. So one thing we need to dive deeper in here, the thing that I just mentioned, the Jacobian. This is a matrix of partial derivatives. So each column here is a partial derivative with respect to the single. Each column right here is the partial derivative with respect to a single parameter delta p, the parameter p. So how can we actually like the role of this is like this is the mathematical core of the Lucas Canade, okay? And this will allow us to estimate like the entire image positional change using a small adjustment delta p. So how does this work? So by calculating the partial derivatives from vector functions like the f1, or the f2, and we can find the rate of change of each variables. And it will answer to the question is like if x or y changes slightly, how does the output will change? So the result here, it will tells you exactly like how adjusting the parameter p changes in the x and y coordinate of the image. So previously, we defined the Jacobian as the partial derivatives of the raw function w with respect to the parameter p. So now we look at the concrete example, which is the affine transform here. So the calculation here is to perform a partial differentiation, to perform partial differentiation, especially on the w. And then we will calculate like the rate of change for wrapping and deformation. And next up, we will solve for the delta p. Next up, we will solve for delta p right here. So after all of the above calculations, what are we solving for? We're solving for like the delta p, okay? So the goal here is to find the optimal adjustment delta p. So by using the Taylor expansion and the Jacobian, we will solve this value to update our parameter p. And this is a detailed explanation of this formula. So the x here is the pixel coordinates, which is like the 2 times 1 vector. The w here is the raw function mapping the template coordinates to a new image coordinates. And the I outside here is the image intensity after the transformation of the scalar. And the nabla I here is the image gradient. And this is the Jacobian matrix that I just introduced. This will be like the 2 times 6 for the affine transform. The delta p right here is the incremental parameters we are solving for, which is like the size of 6 times 1. And the tx here is the template intensity. Template image intensity is also a scalar. So overall, this equation converts the nonlinear image wrapping error into a system of linear equation to solve for this increment delta p. So the original problem is nonlinear and difficult to solve. And then we will use a Taylor expansion to linearize it. So it will allow us to find the optimal update delta p like much more efficiently. So since this is a nonlinear optimization, we focus on the linearized version. So our goal is to calculate this delta p. This is the precise correction needed to align the image with our template. So by rearranging the terms and grouping the variables, we can formulate the equation like this, like as shown here, and setting the stage of a standard linear solution. So, and then it look exactly, I mean, like before including this, when we look at this, it might be struggle to see, but like when we convert into a simple form like this is actually like a standard problem in linear algebra. So the A right here is a constant, correspond to the number I, multiplied by the Jacobian, or the image gradient multiplied by the rough Jacobian. And these are our known constants. The x right here, also known as, is an unknown variable delta p. And the p right here represents the error, which is like the difference between the template and the current wrap image. So By transforming a complex image alignment problem into a much simple problem like this in the algebra, we can actually like solve it using like familiar linear methods. So we will start at the much more familiar concept right here, which is like this least square approximation. So to minimize this, the optimal solution is this. So by applying this into the Lucas-Canade framework, our goal is to find a delta P that can minimize the square error. So the updated rule will become like the thing as you can see on the screen right here, which is H is the Hessian matrix, acting like this term in our linear system. So for an affine graph, this is like a 6 times 6 symmetric positive definite matrix. So what about the matrix that I just mentioned? Mathematically, this is like something that pretty like terrible to look at because like it's so complex. But it's actually like just simply calculated by taking the product, by calculating the product of the image gradient and the Jacobian, the product of the image gradient and the Jacobian, and then you will take. So this matrix will measure like the curvature of our arrow surface. So in plain terms, it tells like how sensitive our cost function is to changes in each parameter. So a well-conditioned Hessian will allow us to find a stable and accurate data P, so which will ensure alignment converges reliably. So we have all of these things. So what does this equation actually mean? We want to find the parameter P right here that makes the wrap image as close as to the template image, the TX, as possible. So since the direct nonlinear search is hard, we will assume that we have a decent initial guess for the P. We have like an initial guess for the P and look for a similar increment data P. Okay. So by using the Taylor expansion, we linearize the wrap image term, and this coincides turning a difficult nonlinear search into a solvable least square problem. Is the extent of the Lucas-Canade algorithm. So this entire process is known as the Gauss-Newton nonlinear optimization. So unlike the standard gradient descent, the Gauss-Newton uses second-order information via the Hessian matrix to take more informed step toward the minimum. So, but however, like a key requirement is that like your starting point must be like relatively close to the solution to ensure accurate conversions. And the Lucas-Canade is essentially the application of the Gauss-Newton method to the specific problem of image alignment. So, and then we will summarize all of these algorithms. The Lucas-Canade algorithm in 7 steps right here. The first one is a wrap image. So the wrap image means that we apply a current parameter P to wrap the input image, and then we will compute the error image by subtract the wrap image up here from the template image TX. And then we will compute the gradient. The gradient is using the nabla operator. And then we will evaluate the Jacobian, this right here, which determine how the wrap changes with P. And then we'll compute the Hessian matrix, the H, which is a very complex matrix. And then we'll compute the delta P in this way. And then we'll update the parameters simply as this. Okay, so beyond the standard additive method, like researchers like Harisham and Sliziski, sorry, I don't know how to spell that. They propose the compositional alignment as an alternative way to update parameters like much more efficiently. So assuming that we have a good starting point like this, we want to find this I in the whole total image. And we assume that we have a good starting point. I don't know how we can assume that, but just like assume that. So how can we actually speed up the process? So let's look at some search strategies to find the local minimum like even faster. So in the traditional additive alignment, we start to form an initial point and continuously update the parameters by adding like small perturbation data p to our current stage in each iteration. But the compositional alignment right here, which involves like a step-by-step adjustment process. So while the additive approach like adds the parameter directly, this method has a different starting point. It will apply the update to the image geometric wrap. We will first apply a wrap of data P to the image and then apply a second wrap. First, we'll apply this wrap and then we'll apply the second wrap using the old parameters P to compose like a new result. So the advantage of this is like this can be more stable this one will converge like faster when still use certain optimization techniques, and this actually converge faster than this one. This one will use a single wrap and this one will use like a second wrap. That's the difference. So to visualize this is the additive strategy. This is like a playing golf. If you hit the ball, of course, you have to go back where you started and try to hit it again for the correct path. But for the compositional strategy, it's like hitting the ball from where it's currently landed. So you can simply like continue the progress from your last position without resetting. This can be visualized like this way. The difference between the additive and the compositional. This only use like a single wrap, and this will use like the second wrap. Okay, just a second. All right, that's enough. Next up. So I will introduce the compositional alignment. And in this framework, we introduce like an incremental raw function, this. Instead of just like adjusting the P directly, we will instead of just like adjusting the P directly, we overlay a small deformation like a fine-tune rotation or shift onto the existing transformation. So what's great about this compositional form? So this is a comparison between the additive alignment and the compositional alignment, and this is its linearized form. So the primary function of this method is it allows us to pre-calculate the Jacobian, right? Which can speed up the process through parallelization. So since the Lucas-Canada alignment involves like constant iteration, the compositional alignment gives us a very practical advantage. The Jacobian does not need to be recalculated every round. We only calculate it once and then reuse it repeatedly. And they can actually significantly save like computational costs. So this is the whole difference between this additive alignment and the compositional alignment. So our goal is the same, to minimize the sum of square error or the SS. And next we will use next up we will use like first order Taylor expansion like previous. So we can linearize the equation. So what is the key here? So we split the RAF function into two parts, right? We split the RAF function into two parts. And then this is the blue arrow represent the additive alignment. And the green arrow here represent the compositional alignment, because we only perform the Taylor expansion on the small update or the correction nearly identity. So the Jacobian remains fixed and does not change with the P. Therefore, we only need to calculate the Jacobian once at the very beginning and use it thereafter. This is like the massive advantage of the compositional form. Oops, sorry. And then this is the lookup candidate, which is the additive alignment I just introduced. So there are two differences in the compositional alignment. The part that changes is the Jacobian section. The key difference here is that we do not recalculate the Jacobian for every parameter updated. Instead, we only use the partial derivatives of the identity wrap because it remains constant. In addition, in this approach, it is not simple additional parameter. It's rather like a compositional update, a RAF function itself, like this. So there are two differences from the compositional alignment compared to the additive alignment. So is there any other way to speed up like this process even further? It's actually yes, of course. This is the inverse alignment, which introduced by Baker and Matthew, or it also called the Baker and Matthew alignment. So we previously mentioned two methods, the additive and the compositional. So their commonality is that the wrap is always applied to the original image IX, while the template TX here is still it remains fixed. So there's a very natural question: why don't we apply the wrap to the template TX instead of the image IX? So this is led us to the next method called the inverse compositional alignment, when we're swapping like the T and the X. So to put it simply like this is the compositional. It's like when we are constantly like adjusting our own viewpoint, to look at the image. In contrast, the inverse compositional, like we pretend that we aren't moving at all, and instead we will let the template itself, have to move to align with the image. So it's like this. This is the compositional strategy, right? You will start from after you finish the first shot. And the inverse strategy means that you move like after you finish your first shot right here, you will normally like start from here, right? And then we will like you will start from here so the ball can hit the hole. But in the inverse compositional strategy, you will assume that you can actually move this hole to that spot. Another question: what is great about the inverse compositional? So in this approach, mathematically way, beyond the fact that the Jacobian right here, beyond the fact that the Jacobian or this term can be pre-computed, but the H matrix, the history matrix, can also be calculated in advance. And this is like a massive jump in efficiency compared to the previous method that we just discussed. So since both the Jacobian and the Hessian can both be pre-computed, so let's look at why. So the Jacobian is now a constant. The Jacobian is now a constant. And the gradient of the template or the number t is also a constant. This is also a constant, meaning we only need to calculate it once at the very beginning. We don't need to update it. So consequently, the Hessian can be also be pre-computed. And then it also become a constant as well. So by pre-calculating all of these components, we can achieve like a significant acceleration in the overall alignment process. This is the Lucas-Canade method, or the additive alignment. Compositional alignment, where we modify the 4 and the 7 term. And this is the inverse compositional alignment. You can see you can change the here. All of these are basically like constant, which means that we only need to calculate it at the very beginning. And this is a comparison of those methods. So in summary, by shifting like the computational burden to the template side or the TX side, the inverse compositional algorithm become much more efficient and significantly faster than all the other, like the additive, the compositional, or the inverse additive methods. Next up is the KLT, or the Canadian-Lucas lactomycin methods. So this is a complete tracking system composed of two parts. The first part is the Lucas-Canade here for the tracking, and the Tomasi for the feature selection. The Tomasi is for the feature selection. So first we will use the Tomasi method to identify the points. We identify the points that are well suited for tracking. And then we will use the Lucas-Canade right here to find the corresponding position of this point in the next frame. So in short, there are two processes. The first is the selection using Tomasi, and the second is the tracking using Lucas-Canade. Moving to the next part, moving to the next section is the optical flow. This is actually like the very important part in this whole chapter. Okay, so in this video, you can see the effect of optical flow tracking while a vehicle is moving. The green arrow represent the movement direction of the feature points at the ground as a camera in advance. So another thing here is the odometry, which is the method used to determine a robot position and orientation by analyzing the related camera images. So by calculating the optical flow or the pixel motion vectors from consecutive images, we can further reconstruct the inverse depth of each point, and this allows us to estimate the camera spatial. Sorry, no, this is too long. You don't need to. So this allows us to estimate the camera spatial position and pose. So why the surrounding point cloud is just like you can actually like reconstruct the 3D scene. So regarding the image alignment, as I just mentioned a moment ago, there are two primary methods to consider: the forward additive and the inverse compositional. And when it comes to tracking in the video, there are four classic technical choices. We have the KLT, the Lucas-Canade and Tomasi for sparse feature tracking, the mean shift for global appearance-based tracking, and the Kalman filter. You might hear Kalman filter before for temporal filtering, and the SLAM for complete mapping and localization. Each of these is a classic technique, and it is important to choose the right tool based on your specific task requirements. So in the assignment, this is actually also a part of the third homework, the homework 3. For your assignment, the result will be represented using arrows like this, So in these two images, hold on. The result will be represented like using arrows like this, okay? In these two images, you can see a perspective shift of object moving within two scenes. I mean, to the human eye, like this, like for image like this, to the human eye, you can actually like notice like no differences between these two frames. So The right arrow, this will point out like the pixel movement between the two frames, which we use to generate the optical flow vector map as shown below. So this vector field at the bottom acts like a fluid field. Like it will demonstrate exactly how the pixel flow across the image. So we will define the problem like the optical flow aims to solve like how to estimate the motion of each pixel given two consecutive frames, or in other words, it is like a pixel level motion estimation methods used for action tracking. So camera ego motion like visual odometry and finding correspondences, which is like a foundation of stereo matching. So to solve it, we rely on two key assumptions. The first is the brightness constancy, and the second is the small motion. So what exactly is the optical flow? So in this diagram right here, we have two adjacent frames like this. This on the left and this on the right, of course. So every pixel can move independently. So we need to estimate that movement. How can we actually estimate that movement from this into this? So this is a different from 2D global transformations like the affine or the projective graphs, which we assume that all points are governed by a single transformation matrix, essentially assuming the entire image like rotates, scales, or translate together. So there are two primary assumptions. The first is color constancy, assuming that within a short period, the brightness of the pixel doesn't change. And the second is a small motion, assuming that the movement of objects of the camera between two frames is very small. So we will observe the surrounding pixel to see if they have the same color. In the next image, we look at the nearby point with the same color and infer it as is the continuation of the same point from the previous frame. So this slide will illustrate the most core and fundamental assumption in optical flow, which is the brightness constancy. This states that while a point in a scene may appear at a different location over the time, its brightness value or color remains unchanged. So mathematically, we can write this like the intensity I of that point at the time t is always equal to the constancy. So following the brightness constancy, let's look at the second assumption, which is the small motion. So what is small motion? This means that in two consecutive images, the distance of pixel moves is extremely small. The distance that both of these move are extremely small. So by using this assumption, we can linearize the brightness constancy constraint. And then we will, in this slide, we summarize the mathematical model derived from our two basic assumptions. We assume a point and move within the image over the time, but its intensity must remain the same. And by using the chain rule to take the derivative of the intensity function respect to the time t, we can get like the following equation like this. Next. So if the displacement is very small, we can treat it as the linearized function. So at the time t plus delta t like this, the intensity of the pixel at the position like this is equal to the intensity of the at the position of the original position over the time. So if the time difference in the delta t is small, we can apply a Taylor expansion to the pixel intensity for linear approximation. Like this, we can use Taylor expansion for this derivation. So let's look at the step-by-step derivation like this. First, we will start at the brightness constancy assumption, and we apply the first order multivariable Taylor expansion like this. And then by arranging the term, you will like eventually have this. So there are actually different ways to write the brightness constancy equation. And the second form right here is the most common shorthand. In here, the ix here and the iy here are the image gradients in the x and the y direction. And the IT here is the change in the brightness over time. And the UV here, is the optical flow vector that we want to solve, representing the velocity of each pixel. The third version here is in the vector form. So we will move the mathematical aside for a moment, so we can look at what each term here. So the IXU here is the image gradient in the x direction, representing the horizontal brightness change. U is the flow velocity in the x direction. Similarly, the IY is in the y gradient, and the V is the velocity in the y direction. And the IT here is a temporal gradient. The temporal gradient represents the rate of brightness change in pixel between two frames. So to solve for this, we need to calculate the derivatives. First one is the spatial derivative. These are the gradients. These are the gradients in the x and the y direction. So we can use like various methods like forward difference, like the Sobel filter, or the derivative of Gaussian filter. So the core idea of this is to observe how much pixel values change relative to its neighbors. The larger the change, the larger the gradient. And the second thing here is the temporal derivative, the IT. It represents the brightness this represents the brightness change over time. So typically we will use frame differencing, which involve like subtracting one frame from the adjacent one to see how much the brightness at the pixel has changed. So when we calculate the brightness change over time, the most common way I just mentioned is the frame differencing, also as like forward difference. So this diagram is look like when we like the frame one minus the frame two, like when we have this one. But in this, we'll take the example like this. This is the image at the time, the image I at the time t. The middle one is the image I at the time t plus 1. So by subtracting the first one from t to t plus 1, we can get the difference on the right hand side like this. But the difference is like when you like subtracting from this region into this, we have the 9 here, which is like the 10 minus 1. So this difference is a temporal derivative. This is called the temporal derivative we need for the equation. So once we all have these values, the x and the y spatial gradient, and the IT, we can represent the optical flow using the traditional equation I just showed before, like this. This is the traditional equation. So the focus of our solution lies in the unknown optical flow vectors, which is the U. This, we don't know this. This represents the velocity at which the pixel move in the x and the y direction over time. And in our model, the U and the V, we need to estimate that we don't know that. So to summarize, we will calculate the Ix, the Iy, and then we will solve for the U and the V to estimate the motion of every pixel. But we cannot actually like solve for optical flow directly. We can actually not solve this directly because it isn't like there isn't like an unique solution. We are faced with an infinite number of possible solutions. There are infinite solutions. So find the correct one, we need to introduce like additional information or any for other constraints. So our main investigation from here is we'll be focusing on how to find these the specific values of the U and the V, because the Ix, Iy, and the It you calculated before, but you don't know the U and the V. So we need to calculate that. So to find the exact values of the U and the V, we introduce different constraints like this. So generally, these are categorized into two main types, which we will discuss next. The first one is the Hornström optical flow, and the second one is the Lucas-Canade optical flow. The Lucas-Canade I introduced before, but the Hornström, you need this. So the first one I introduced is actually on the right, not on the left, which is the constant flow. The first time I introduced is the constant flow constraint. So the strategy here is to assume that within a small local region, the flow is consistent or constant. So by making this constant flow assumption, we can turn our underdetermined problem into the one that can be solved or solvable. So for example, if we have like a 5x5 small patch like this, which will have like 25 pixels in total, we assume that the optical flow UV of all 25 pixels is the same. So within these 25 pixels, each one has its own brightness, its own brightness gradients, Ix and Iy, and the temporal gradient It, of course. So we can write an equation for every pixel. So by doing this, we will have 25 equations in total, but only two variable unknown, which is the U and the V. So this will allow us to use the least square method to find the best solution. So to solve this system with multiple equation, we will use linear algebra to find the best estimate for our unknown vector x, like this, which contain the U and the V in this. And this is the U. This is sometimes it's called the Lucas-Canade optical flow, because like this term I just introduced in the previous part about the Lucas-Canade algorithm. So you can probably, obviously you can not read anything on the left, but like this image will show the result of dynamic checking on vehicles and pedestrians on a bridge using the Lucas-Canade optical flow method in the UBTV. So you can see that in this one, you can see many color screen on this one. So this line will represent each line will correspond to a track feature point, and the path from the start to the end of the line show the movement trajectory of the optical flow of that point between each frame, and the color are assigned randomly, so we can distinguish between each of the motion trajectories. So when will this actually solvable? We'll have 10 minutes break and we'll come back at 4:20. Okay. All right, let's get back into this. So to solve for this, to solve for the least square system like this, you will need like you will need some criteria like this. The first thing is the ATA right here should be like invertible, because we need like a complete information in the patch. The second thing here is, no, this is not, there's no lambda here. So this relates back to the Harris corner detector that we discussed previously. So let's examine how this matrix affect the optical flow estimation. So in the corners region, both lambda 1 and lambda 2 are very large. This is exactly where the Lucas-Kennedy method performed best. And the corner has a gradient changes in two directions, meaning that the local image information is sufficient and rich in variation. And the corners are ideal location for estimating the optical flow. Only with enough information can we accurately solve for the U and the V. And this image shows the barber pole illusion. So the rotating stripe right here appears to move like vertically, because like our view is restricted through a narrow opening. So like for a narrow opening like this, we're assuming that like this actually like moving like vertically. And this perfectly like illustrate the aperture problem in the optical flow when we only observe 1D edge within a small local patch. And the true direction of the motion is ambiguous. So to resolve this, we must rely on the corners where the gradient changes in two directions. Like this one. Even when you look at this one, can you guess like where is the direct where is like which direction are they actually moving? So suppose that we can only see like a moving diagonal stripe through a small opening like this. But in reality, we cannot like determine if its true direction of motion. So we can only perceive like the velocity component that is like perpendicular to the edge. Like for example, on the right here, a vertical slit makes it like makes the perceived upward motion, and a horizontal slit horizontal slit like this makes it like perceive like a rightward motion. And only a circular opening can preserve like more directional information. Like this, when you can see in here, the vertical slit when we look at in the vertical slit like here, we can see that, hold on. When we look into the vertical slit like here, we can see that it actually like moves like upward motion. The horizontal slit is like a rightward motion. And the circular opening like will preserve like more directional information. So, and this is called the aperture problem. So there's a question right here, like in which direction is the line, the blue line here is moving through this small hole right here? Can you guess like, okay, so first position we have this, second position we have this, like this. So can you guess like which position is this line is moving? Because like it's different like this, so we can actually don't know which position is moving, but it's actually like this. It's actually like moving like upward, but this looks like it's moving like rightward. It's like this. It looks like this. So the thing here is like when you look into the small hole like that, this is the aperture problem. When you see that is looks like it moving like rightward, but it actually like moving upwards. So if you want the patches with different gradients, so we need the patches with different gradients so we can avoid the aperture problem. So to avoid the aperture problem, we specifically like select the regions with rich structure like corner or edges for checking. So this is why the methods like the Harris corner detector are so important. So let's look at the concrete example to understand the aperture problem. On the left is our true image H, which is very simple. The intensity values are identical across each row. The intensity value are identical across like each row when you have like 1, 2, 3, 4, 5 like this. And then this image move down, and to the right by 1 and 1 like this in a coordinate, which is the ground truth. So on the right hand side here is the observed image IXY, where we see the whole thing shift down by 1 row. So in this case, we can calculate the V here, right? But we cannot like solve for the U because the IX is equal to 0, meaning that there is 0 gradient change in the horizontal direction, which means that from this specific patch, we can only observe first vertical motion. And this is the aperture problem. So, and this will refer to the Hornstrong method, which is the focus for the third assignment. So to solve for this density issue, we need like a smoothness constraint. We will introduce about this. So because the object in the real world are mostly like rigid or deform elastically, so and they usually like move like coherently. So therefore, if an object is continuous, we expect its optical flow to be continuous as well. And this leads to a key assumption in the optical flow estimation is the optical flow fields should be smooth. And the Hornstrong methods works by simultaneously satisfying 2 conditions. The first is the brightness constancy, and the second one is the smoothness. We then solve this as a mathematical optimization problem to find the optical flow vector, which is the vector U and vector V for every single pixel. So unlike any sparse method, this global approach is applied to every single pixel in the image. This will apply to every single pixel in the image. And then we'll use like the smooth flow field to compute the optical flow. So how can we actually mathematically represent the smoothness of an image? So when we look at the variation between a pixel and its neighbors, like here, specifically, we can check if there are changes in the gradients of the flow field. So we will consider like which type of flow field minimizes our objective function. On the left-hand side here, we have a random noise flow field where colors are jumped. This means that the difference between adjacent pixel is pretty huge, resulting in a very high summation value. And on the right-hand side here, we'll have like a smoothly varying flow field because since each pixel value is very similar to its neighbors, the total value of the objective function is much smaller. So to minimize the smoothness term, we want the flow field to be like as smooth as possible because we don't want it to be like as noisy as this. So this is a core concept of the Hornstrong method. So, and this is it's clear now that the flow field on the right is much smoother and thus more desirable for global optimization. And now we will combine two different constraints into a single framework. The first is the brightness constancy, and the second is the smooth flow field. And by merging these two, we can solve for a dense optical flow that is both accurate and to the image data in the physical particle. As we just mentioned, the core of the Hornström is the combination of two assumptions, the brightness constancy and the smoothness term. So we will represent this as a total energy function. The first term right here, the ESIJ, is the smoothness term. This which like encourage like the velocity, the u vector and the u and the v to change like smoothly between neighboring pixels. And the second term right here, the EDIJ is the data term. This is the data term or the brightness constancy, which requires the intensity change to be minimal after applying the flow. And the parameter lambda right here is like a weighting factor that controls the balance between these two. A larger lambda means that we prioritize or we emphasize the brightness constancy, while a smaller, if we have like a smaller lambda, we will like prioritize the smoothness term on the left. So our goal is to find the U and the V that can minimize this total energy. So to ensure the smoothness, we compare each pixel with its neighbors. We want the velocity vectors U and the V of a pixel not to differ too much from those surrounding it. So the small diagram right here show like how can we like evaluate like the smoothness in both horizontal and vertical way, in vertical direction. And this term is actually like effectively like penalize like the jerky or noisy transition in the flow field. So we can actually solve for the smoothness term right here within this formula and the brightness constancy in this formula. So how can we actually minimize this energy function? So we will solve this optimization. We will solve this as an optimization problem using the gradient descent or any other similar iterative solvers. So the objective here is to minimize the total error, right? The total error right here, which is the sum of the smoothing error, the smoothness term, and the brightness error or the brightness constancy. So while like the total energy equation like this is actually pretty huge, right? It's a huge sum. It looks like computationally complex. We only need to focus on a single pixel at a time. So to find the way to update the rule, we identify all terms. We identify all terms to related to the velocity UKL at a specific pixel and take the partial derivative. So there are two main components that can affect this UKL. Two main components that can influence this. The first is the smoothness constraint. The smoothness constraint. 4 thing 1, 2, 3, 4 from the smoothness term, which is like the difference between the UL and its four neighbor, like this one. We have like 4 neighbors of this. Sorry. And the second thing is the brightness constancy constraint, which ensures the UKL minimize the intensity error. So the resulting derivation give us like the iterative update of the rule that we need. So as discussed, we use a smoothness term to prevent the optical flow field from changing too abruptly. But how can we like mathematically represent the smoothness? There are some few ways. The most common method is using the sum of the square gradient, meaning that we want the spatial variation of the u and the v in the x and the y direction to be as small as possible. And another approach is using the Laplacian, represented as this term. And So the UKL with head right here is not a head, but is the average of the neighboring pixels, and this ensures that each pixel's flow doesn't like deviate significantly from its local neighbors. So essentially, this is equivalent to minimizing the second order derivative, creating like a much smoother sliding flow field. So after taking all of the partial derivative with respect to the u and the v separately, we arrive at the following system of equations like this. And these equations will allow us to iteratively update the flow vectors until the entire field reaches an optimal smooth state. So we have just taken the partial derivative of the energy function E with respect to the UKL and the VKL, okay? And by setting these derivatives to 0 to find the local minimum, of these, we derive this system into two simultaneous equations, like this. And by rearranging these terms, we can reformulate the entire problem. And this structure allows us to solve like a flow vectors using like standard linear algebra techniques. And so why do actually like need like this entire mathematical derivation? So one thing to mention that the ultimate goal is to find the optical flow vectors, the U and the V. We are solving for the optical flow U and the V by minimizing the total energy. So we identify the specific values that best satisfy both our data and the smoothness constraint. And returning to our previous result, we can rewrite the entire system in a more compact matrix notation. And this makes the relationship between the gradients and the flow vectors much more clearer, like this. And this system of equations can be solved using the inverse matrix method, like this. This is the inverse matrix method. You might study about this in the linear algebra. We can calculate this by utilizing the aggregate matrix and the determinant of our 2 times 2 system. And here is the explicit setup for the inverse matrix. So showing how we can use the aggregate matrix and the determinant to isolate our unknowns. So in the previous slide, we derived the linear system for the inverse matrix. And now we expand those formulas through multiplication to show the exact mathematical form of the final update. And ultimately, we'll arrive at the final update rule shown in the box right here, which we can actually solve for the UKL and the VKL. This is an iterative formula used to calculate the flow for each pixel in each step. And one thing to remind is the lambda. The lambda controls the balance between the brightness and the smoothness. So if the lambda is small, the algorithm will focus the algorithm will focus like more heavily on the smoothness of the flow field. And as a side note, in the original Hornstrong paper, lambda is actually placed on the smoothness term rather than in the data term. So the lambda balance the smoothness and the brightness. So if the lambda is extremely small, this term will dominate the denominator, driving by correction update towards 0. I mean, and this will go to 0. So effectively, the algorithm prioritizes a smooth field over an actual image data. And the result is a perfectly smooth flow field that fails to capture any real motion. So therefore, the final output for the U and the V is obtained by combining both the smoothness term and the brightness constraint. The smoothness term we will solve for 4 different adjacent term, and this is the brightest term. And this is like a short summary of this Hornstrong optical flow algorithm. The first is you pre-compute the image gradient Ix and Iy. Second is to compute the temporal gradients, IT. Initialize the flow field when you set the U and the V to 0. And then you will compute the flow field updates for each pixel using these two formulas. And by using this Horstrang algorithm, you can use it for the homework 3 or the third homework or the homework 3. A thing to remind you that homework 3 just released on the NTU Cool, and it will do in 2 weeks. So you will basically have 2 weeks to solve this problem. In this homework, you will implement this Horstrang optical flow estimation and using this step right here. And then you can for this, like in this assignment, you will use the Lena image, and you will implement the Horstrang optical flow estimation. So the goal here is to calculate the motion vector for every pixel, known as the optical flow, from 2 consecutive images. And for the variable setting, which is the lambda setting, you can set it by this will control like the weight ratio between the smoothness and the brightness constancy. So we need to test 3 cases here, 0.1, 1, and 10. And for the iteration, you can try like from 1 to 64 iterations. So to observe like the difference in the convergence and the overall effect. So to start here, you need to calculate the image gradient, the Ix and the Iy. So when you compute like the spatial gradients and the temporal gradients IT here, for every pixel, of course, the method involves like using the differences in the neighboring regions to estimate like the gradient. And the formula is already provided right here. And which essentially like is like a 3D convolution calculating across like X, Y, and the T. And for the input image, we will use the Lena image to simulate an artificial like translation by shifting the image 1 pixel to the. We will use a translation by shifting the entire image 1 pixel to the bottom right corner to create the second frame. And this way, the ground truth is the flow of 1 and 1, making it easier for us to observe the prediction accuracy. But one thing to note that while the original paper placed like alpha on the smoothness term, but this slide I placed the alpha on the brightness term. Like this, when you shift the original image to when you shift the image to the bottom right, you can have like the second frame like this. You shift 1 pixel like that. This will be like your second frame, and this is the original one. For example, like these. This is just an exact example. This is not the homework result. For example, like this, you will have like an optical flow, a map of which is a set vector like this. So if you loop it through like if you increase the number of iterations, you will have a result like a much clearer result like this. But you need to try the number of iteration from 1 up to like 64. And at the start, after you calculate the Ix, Iy, and the It, the next step is you need to set the velocity vectors, the U and the V, for every pixel to 0. And then you will perform the iterative updates. And we need to apply this update formula. This is the update formula. Each pixels in here will update its flow based on its gradient. And the gradients Ix, Iy, and It you need to pre-compute before. And you need to and we apply the update formula like we derived earlier. Long story short, you only need to do this formula, which you can actually satisfy both the brightness constancy and the smoothness conditions. For example, like this. For the iteration, when you set the iteration to 1, you will have like a result like this. You can see like a small optical flow, small vectors, which is white in this. And when you increase the number of iteration, like to 4, it will start to become like much more clear, as you see. When you increase to a 16, it will have like this. And 64, you will have like this. This is just a reference result for you. Okay, and this is all this thing is for the third homework or the homework 3. You can actually like find this material as a reference in the on the course website. I already published the chapter 9 slide, and you can actually like find this in here. So when you, because like we want to test the iteration from 1 to up to 64, you can see like it's a reference right here. When you increase to 4, it will be look like this: 16 and 64. So to save on the circuitry and achieve like a higher sensitivity of fill factor, many like CMOS sensors out there, especially like those in your mobile phones, utilize a thing called the rolling shutter. But like fast scenes or camera motion can cause like significant like the distortion, which is making straight line appear curves, which you usually see in the helicopter propellers. So to compensate for this distortion caused by varying exposure times across scan lines, we must estimate precise like per pixel optical flow. Establishing a robust rolling shutter model is also critical for achieving accurate pose estimation from the motion. And moving to much more modern methods like the RAF or the recurrent all pairs fields transform. This is like a state-of-the-art deep learning architecture for the optical flow, and it extracts per pixel features and construct multi-scale 4D correlation volumes of all pixel pairs to iteratively refine the flow field. So by processing these 4D correlation volumes, the RAF is iteratively refines the flow field, and this allows the network to handle both small and large displacement with high precision and robustness. And the third section here we'll deal with is the parametric motion.
You can play a joke, yeah, because section, yeah, play a joke.
All right, that's all. Next up is the third part, which is the parametric motion.
Parametric.
Parametric.
Yeah, parametric.
So while the traditional optical flow methods focus on finding the minimum displacement through intensity differences, like here. The author here in this paper, they propose an alternative approach,
Alternative.
alternative
Yeah,
approach
alternative.
to model the motion.
Mhm.
So in this model, the motion trajectory is the motion trajectory of the specific point is evaluated based on the weight. Is evaluated based on the weight of its surrounding grid points, like this. So specifically, a point UI like this is calculated as a weighted combination of its neighbors, like this. Is calculated by a weighted combination of its neighbors. And the weight function B here, the B here is a weight function, which is the basic function, can take like various mathematical forms, like here. You can take so many mathematical forms like here, depending on the required smoothness. For example, it can be a block, or it can be like linearly like this. And by employing different basis function, we change like how the motion is measured. Essentially, we are adjusting the weighting strategy to better estimate the distance of an object has moved within the optical field. And for the spline-based motion can also be used to correct the lens distortion. This includes fixing fixing pincushion like this, or barrel in a convex way distortion, where the straight line appears to wrap inward or outward. Because when we look into because this is undistorted, and when you look into this, all the straight lines appear to wrap like inward like this or outward like this. And in medical imaging, motion estimation is critical for correcting misalignments. So since organs are constantly moving or pulsating, we will use neural networks and registration techniques to accurately find an aligned regions for diagnosis. And for the final section here is the layered motion. These two section is actually much lighter than those previous. Is mathematically heavy. So visual motion is often like caused by a small number of objects located at different depths. And this means that the magnitude of the motion is not uniform across the scene. The means of the magnitude of motion is not uniform across the scene. So the objects closer to the camera move differently than those in the distance, like this. The objects closer to the camera will move differently than those in the distance. And in many cases, motion is driven by a few distinct layers of at various depths. And because of this, the displacement of every object is not the same, which leads us to the concept of layer motion, like this. So by analyzing motion trajectories and optical flow, we can effectively distinguish the foreground from the background. Like this, we actually distinguish between the foreground from the background within a single video sequence. And the process is actually start with the optical flow analysis, which I just introduced before. And then we will use the k-means clustering to group the similar motion vectors. And then after multiple iterations, we obtain the final layers that allow us to segment and separate the foreground and the background into distinct categories. And another thing we need to mention here is the reflection. And this slide will cover the reflection separation. And in cases that where we see reflected images, like when we see through a window, the goal is to determine if we can actually like mathematically reconstruct the original and individual images. For example, like in a scene with an observers, for a scene like with an observer see like this, and the reflected subjects A or C, A and B, which is the reflected subjects, and this is the observer C. We can process the layers to recover the true appearance of each subject, like the D and the E here. By like when we can actually like separating like the reflection from the background. And that's all.
Okay, you can play a joke and then you can present your research. Yeah.
Let me just wait here. I will go here. Yeah. Sorry. Sorry to interrupt.
Okay, let me ask the student. Okay, 贺少伟，你现在在吗？贺少伟，那个你的话，那个 Turn Project 的报告你没有来那个报告哦。哎，贺少伟，你如果听到的话，那个回一下。OK，贺少伟，有听到吗？贺少伟，我看到你麦克风有开了啊，你有听得到我们讲话吗？听得，声音好小哦。你那个大声一点好吗？对，贺少伟，大声一点。可以听到我们讲话吗？听得到，好 ，OK， 好，那你记得要来报告你的 Turn Project 的报告的进度哦，哈 ，OK，you can go ahead， yeah.
Okay. All right, so next up I will present my research, and this might appear in your final exam, so please pay attention to it. And in this research, I will do the ternary quantization for the large language models. And when we talk about like this, we talk about like the quantization of the large language models, is actually not like in a normal way. This is actually like in a pretty extreme way.
Yeah, please add your phone number. Okay. Okay, so same thing for his research. Yeah, we will have 6 points on his research, 2 points on the method, 2 points on the step, and 2 points on the result. Okay. Good. Okay.
So the goal here is to compress the llama to 7 billion. This is a large language model from Meta. You guys might heard about like some multiple large language model out there, but I only use this llama to 7 billion. This is actually like pretty outdated actually, because it is 3 years old. But I use that to experiment on my algorithm. So the thing is, like when we need to deploy the large language models into the edge devices or into a chip, you need to quantize it first, because the large language model itself is actually like pretty like the size is actually pretty large, pretty heavy. So you need to quantize it first. So for the quantization, you usually like just rounding the weights to the nearest integer. But in this case, I will quantize it down to the ternary states. And to do this, I will modify modify the omniquant algorithm, so I can actually like have that 3 weights distribution. So the thing is, as I mentioned, the modern AI models, like it will be like computationally heavy, and because it uses like 16-bit floating point or the FP16, and all the matrix multiplication, like when you multiply the input to its weights, it will be like pretty heavy, and it will be causing like high latency when you deploy into the chip or into the edge devices. So we need to quantize it first, right? When we usually like quantize the FP16 down to like to the 8-bit state, 8 bits or 4 bits or even 3 bits, but like those are not like it's usually like when you quantize it down to a very like in an extreme way, it will cause the model to become like more it will be collapsed. And in this case, we need to quantize down to the 2-bit. And when we quantize it under 2-bit, it actually like cause the model to start collapsing. But in this case, I will even push that in a more extreme way, which only has 3 states. 3 states means that all of the model weights will become only 3 values, which is the -1, only the -1, the 0 and 1, which is like only have these value of state. And why are these 3 states? These states are called the ternary values. Ternary values means that when you have the weights of only these 3 values, all of the matrix multiplication will turn into a very simple additions and subtraction, and it can drastically like cut the energy use, and the model size is also become much more smaller. So how to quantize the large language models, you might use like the q8 or the quantization aware training, but they can actually use a very high accuracy, but it needs to retrain the entire model. It needs to retrain the entire model, but I don't have, we don't actually usually have like that much resources or massive data set like that. So a more alternative approach, a much more easier approach is to use the PTQ. PTQ means the post-training quantization, means that we don't have to retrain the entire model. We already have that model, and we do some mathematical operators into the existing weight. We don't have to retrain it. So the thing here is, when we quantize the model, we will normally use the round to the nearest integer approach. But in most cases, it will destroy like some critical weights. So since then, the model will collapse, and then I deploy like a more optimal way to do that. And the method I'm doing here is called the OmniQuant. This method is developed by the OpenGV lab, and this will treat the quantization as an optimization problem rather than just like simple rounding. So the goal here is to minimize the mean square error, or the MSE, also in the chapter 9 before, between the FP16 output and the quantized model output. And we're not just like simply like rounding the number, like I just mentioned. We will use like a small randomized subset of the Wikitext2. Wikitext2 is a text data set. So we can use this to calibrate, like, so we can use like a small subset of the Wikitext to use as a calibration data to support for the quantization process. So the optimization mechanism here, we will use 2 learnable parameters. The first one is the learnable equivalent transformation, or the LET. This we can calculate the scaling factor S to smooth out the activation outliers. And the second learnable parameter is the learnable weight clipping, or the LWC. And by using this, you can actually calculate out the C value, or the clipping thresholds. So we can ensure that critical information is preserved before rounding, because we need this C to cut those outliers off. And this is the quantization equation. It's actually pretty simple. The W here is the original floating point, the 16-bit floating point weights. You multiply it by the S term, which is the scaling factor here, and divide it by the divided by the C value. And then you will need the Qmin and the Qmax. The Qmin and the Qmax here means that you can actually the Qmin and the Qmax is predetermined. You can set that Qmin and Qmax is just like a range of the weight that you want to quantize it down to. So to achieve the ternary state, we need to force the Qmin to -1 and the Qmax to 1. And by using the symmetric mapping, we can actually force it all the weights down to only 3 values, -1, 0, and 1. So with these only 3 values, you can actually achieve multiplication free, only simple addition and subtraction in the hardware level.
Previous and previous. Okay, so what's the value you use for S?
They are calculated during the.
Yeah.
It is not predetermined. It's like the weight you will need to. It will be calculated during the quantization process.
Yeah, that's fine. So this C is also calculated, right?
Yeah, they are all learnable.
Both of them are calculated. Then let's go to the example.
Which example?
No. Page turn, yeah, page turn, and page turn. Page turn. You have the.
This is a shortened version, Professor.
I want the.
You want the complete one?
Yeah, the complete one, which has the examples. Yeah. Okay, so over here, you should add the S and C over here.
You cannot have the SNC here because like you divide the weight into multiple group and multiple blocks, and you will have so many SNC.
Yeah,
and that doesn't mean-
I'm saying specifically this sentence. When is what's the S and C for this one?
you cannot have. I mean, like you can have that, but like including that term into here, it means like it doesn't mean that much.
I know, but still, we okay. So please add. Let's do it now. Yeah, let's do it now.
But I don't have the SNC here.
I know. I mean, just try to find it. Yeah. And first of all, add your mobile phone number.
In this.
Yeah. Good. Good. Okay. And then let's go there. Yes, for this one, ternary. So over here.
You need the S and the C.
Yeah, let's edit. Let's edit right now.
But there are so.
I know. Just follow my instruction. Yeah. Okay, over here. Come on, yeah, space. S equals. The equal sign.
Wait a second.
Oh, you need that keyboard because one of the key is broken.
Yeah.
Oh, I get it. Equals question mark. Yeah, and comma C equals question mark. Yeah, comma. Yeah. So edit. Okay, and the next example. We have 3 for this one. Yes. Copy that. Yeah. Okay, 2-bit also have that. 16-bit also have that.
No, they don't have that.
Yeah. Does 2-bit also have that, or only your ternary has this?
Only the ternary because no, the 2-bit also have that.
The 2-bit also have it.
Yeah, because this equation can actually apply for the 2-bit and the ternary also.
For the 2-bit and your ternary, right? That's good. Okay, and then next page. Yes, this. Okay, going good. And our ternary over here at the S equals. Yeah. Good. That's good. That's what I want. Okay.
But you cannot have
okay,
this.
Good. Yeah, and then the next example.
No, I will include 2 examples here.
Okay, please add one more example. I like examples. Okay. Let me state it up. Okay, science is repeatable. Repeatable means this experiment parameter quantization done by Nam-An is all the details are included in the report, and then Wanxuan take this report and go to New York, and she can follow your instruction and all the parameters. Then she can repeat your experiment. That's repeatable. Okay, that's science. Okay, and if you something that you can do and Wanxuan cannot repeat, do you know what's the name?
No.
That's called witchcraft, because you are a witch. You can do something and Wanxuan cannot repeat it. That's witchcraft. Okay, that's not science. Understand? So science is that your report has to be so detailed, so complete that Wanxuan can repeat it in New York. Understand?
But like this this S and the C is not that necessary to include in this.
We do also have to use the other example. The other examples, yeah, like the why not correct, right? Yeah.
This is only for the the multiple choice questions.
Yes, but this also have your S and C, right?
No, the S and the C is the S and the C term is for the model. It's not about the examples.
So you are saying the same. First of all, let me ask you, the same S and C for this one and the same S and C for this one, right?
The S and the C is in the model.
I know, but is it the same for this one and this one?
Yeah, they're all the same.
They are the same, and also the same for this one. Yeah. So then you have to say that. So when in your example, you have to say that. Okay, and if they are different, you have to write every S and C. Yeah.
But that S and C it doesn't have that much like.
You have to write it so detailed that Wanxuan can repeat it in New York.
Because like all the weight will be quantized down to the. Okay.
Yeah. She has to get the same result using your parameters. She has to get the same result. Yeah, it's repeatable. That's science. Yeah. And if you can do it, and Wanxuan cannot do it, that's witchcraft. You are a witch.
But what will happen if I want to become a witch?
Well, if you want to become a witch, that's fine. But you cannot get your expert degree because you will get the witch degree. Yeah, not the computer science and information engineering degree, master degree. Yeah.
Okay, so all of these experiments are conducted on a single NVIDIA 5090. And I will use 4 different data sets to evaluate these experiments. These 4 data sets, I will use the Wikitext2.
The complete version, so you can go to the example. Yeah.
But the complete version doesn't have the summary for the students to.
You can copy that or show the summary at the end. Yeah. Yeah, I like the complete, especially the examples. Yeah, so that the students know what you are working on. Yeah. The example. Yeah, let's go to the example. Yeah.
For example, like the Wikitext2 data set here, you will have like 44,000 examples of short paragraph like this, and the model will have to like to predict like what will happen next after this word. So after this word, you can actually like see like this example of like these 3 versions. The IP16 is the original one, the 2-bit and the ternary, and they're actually pretty different from each other. I mean, this is just an example, and it will differ every single time you rerun it. And this is a ground truth. So this text is like not about like the not about like when you need to measure the accuracy like because like for the large language model, if you ask the model like 10 times, all of those 10 answers will be different from each other. So we will use the Wikitext2 dataset to calculate the perplexity, and the perplexity is something that I will introduce later. And just like these examples, you will have different like prediction like this. And this is the ground truth. The ground truth is the original paragraph, and it actually like it's unfinished, and the model needs to predict like what will come like after all of these words. So by having the model's prediction, you can actually like measure like how confident or how confused the model is after predicting all of those answers. And beside the Wikitext, we will have the Green Grande dataset right here. This dataset is like a fill in the blank problem. So you will have like a sentence or paragraph like this. It's like a fill in the blank problem. So you have 2 choices, and the model will have like to choose between these 2 choices to fill in this blank. So we can actually measure the accuracy from from those choices of the model. Next up, we will have the helix walk data set. This is like when we have like a context like this. This is like an unfinished sentence when you have like you need to fill in something into here. And this also you have like multiple choices, and the model will need to choose like which is the correct answer of this. And for the AI, and another task is the ARC or the AI to reasoning challenge. So these are like science questions like this, and this is also like a multiple choice questions. You will have 4 choices, and the model will have to choose like between those, and then you will calculate like the accuracy of that. Then this is how you like measure like the accuracy of this. So for the perplexity, for the metrics I use to evaluate these, we will have the perplexity, the accuracy, and the length numeric accuracy. The accuracy is the percentage of like how many times the model will predict like correctly among all those answers. And the length numeric accuracy is like because the large language model like it have like a natural bias toward like predicting like shorter sentence. So this will divide by log probabilities, so we can ensure like for tasks like that has like long answer, we will still like evaluate them in a more fairly way. So what is the perplexity? The perplexity
Okay,
is
we can explain this next week because today it's already 5:20. Yeah. Okay. So that's all for today. Yeah.
and by the way, is in the slides that uploaded into the website, you can actually find the summary in that. Because like this is my complete version, I don't want you to see the complete version because there are some confidential information in that. And you will have like this. You will need to study this for the exam. In short, okay, you if you look into like any other slides, that will be okay. You can know more something about that. But if you only care about the exam, you can only care about like the last slide. This is also updated on the website. You can actually see that. Okay, thank you everyone for your attention. Bye bye.
Nguyễn 老师好，喂。